Okay, so my name's David. I'm from OSU. I'm in the research center with Dan, and we're going to talk about the same thing. I think I'm the third person today to address superalloys for power plant construction. My particular part of the project is sponsored by the Babcock and Wilcox Company. So what I'm going to talk about is first post-weld heat treatment, and then some stress relaxation cracking testing work I've been doing. So to start off, the motivation, just like the rest of the motivation for superalloys and power plants, is to increase the operating conditions, of course. So this naming scheme is advanced ultra supercritical, referring to the steam conditions. This is supposed to increase plant efficiency because the temperature change of the thermal cycle is greater. So the plant's more efficient. You can have burn less fuel and have less harmful emissions. Here are some of the requirements. The way we've gotten to AUSC is based on the steam conditions. So this is where steam is a subcritical fluid and a supercritical fluid. And I think you can get to ultra supercritical through plant design. And then in order to jump, though, to advanced ultra supercritical, we have some materials considerations, which is why we're studying superalloys for power generation. Another way to illustrate that is perhaps one of my favorite graphs, which has to do with, this is actually temperature for rupture in 100,000 hours. And so we have some common power plant materials here. And as you can see, based on the requirement of 760C and 100 MPa, you're really limited to these precipitation strengthened nickel-based alloys. Another one I'm going to talk about is this alloy 617, which has been considered for use at 700C. So here are, to introduce those alloys some more, the nominal compositions of these alloys. This is 740H. It's been through a composition modification from 740 to H, and some of the changes there were balancing the aluminum and titanium ratio to work on the eta-phase precipitation problem. I think niobium and boron were reduced because there was some liquation cracking. Anyway, some key things to note here are the differences in molybdenum content and niobium and carbon and boron. Those are all going to be relevant to keep in mind. I should point out, so molybdenum, of course, is a solid solution strengthening element, which is going to make it more and more difficult to make forging such as this. This is a 740H pierced and drawn billet. Here are the dimensions. This is made at Wyman Gordon. And I think it's only been made, a pipe of this size of such an alloy a couple times. And so 740H is favored because of this low molybdenum for the forging and also coal ash corrosion resistance. And it was also designed for this application where alloy 282 wasn't really. It's just been found that it's pretty applicable. So some of the motivation for this work has to do with the creep rupture strength and, of course, the weld metal weld strength reduction factor Dan mentioned. So this slide helps really visualize those implications. So such a pipe of a stronger material like 740H could have a much larger ID with a much smaller pipe. And so this obviously moves way more steam. Of course, you would lose this advantage with the weld strength reduction factor or with a alloy which is not as strong. The real motivation, though, because so we can account for a debit in weld strength but with wall thickness. I mean, that's not an ideal solution, but that's a solution. The real motivation, though, would be premature cracking. So premature cracking was actually found in a test plant made of 617 and operated at 700C, and there were cracks discovered via steam leaking all over some of these major weldments. And so that's pretty concerning because this is not as predictable as a weld strength reduction factor. It's a multiplicative factor of like 0.3 or 0.7, 30%, something like that. So you can plan on that, but you can't plan on this. And so that makes it, I think, a little bit more worrisome of a problem. Um, the issue here is supposed to be stress relaxation cracking. So this occurs by concentration of stress at grain boundaries, often associated with intragranular precipitation. So of course there's stress concentration at grain boundaries anyway, but if the grain interiors are strengthened by precipitation, such as in the case of these nickel-based alloys which form gamma prime, there's additional stress concentration at boundaries. And so that when we're talking about stress concentration at boundaries, the other thing you can think about is boundary area in a given volume. So you can imagine if, like in this schematic here, these grains are all way bigger, the stresses on a boundary would be much higher. Another point to make as we go on the list here is that, so cracking was avoided in 617 with a post-weld heat treatment for like stress relief around 980 C for 3 hours. This has also been found to improve the ductility in a slow strain rate test, which is targeted at this stress relaxation cracking problem. So here we have a little schematic of the problem. So we have, of course, a welding thermal cycle, and then it's not followed by a homogenization and stress relief. It could be, this is the ideal case, but it's not too practical, certainly not desirable to do this. If this can be skipped at all, that would be ideal. But if you do not skip this, you never heat above the aging temperature range, the stresses can't fully relax. And so then when you finish your post-weld heat treatment and go back into service, you have this risk of the residual stresses and the normal operating stresses adding in a cumulative way to accelerate creep failure and perhaps leading to a problem like this one. So, of course, the solution is to have a high temperature stress relief post-weld heat treatment. But I'll talk more about that. So first, I'm going to talk about some different post-weld heat treatments. The ideal, or the current case, is to simply age this material with a one-step aging post-weld heat treatment, which as we just heard, is not what you're supposed to do with alloy 282, but in this AUSC project, this is the standard aging post-weld heat treatment. And so there's some other heat treatments to consider, which are a higher temperature age, such as this one, and then some two-step heat treatments, which do involve homogenization. And so before I go into relaxation cracking testing, I'll go over the microstructures generated by those post-weld heat treatments. So first of all, in the aging condition, directly aging, you'll have the effects of microsegregation going to become still very apparent. And so there's the precipitate free zone problem, which Dan already covered and Professor DuPont covered. And there's also just the general gamma prime distribution inhomogeneity from dendrite boundaries to dendrite cores based on the partitioning of precipitate forming elements. So that's the direct age heat treatment, which we attribute most of the poor creep rupture properties to the precipitate free zones, I believe, but there's also this inhomogeneous gamma prime distribution. If you do a higher temperature aging heat treatment, such as the one that successfully relieves stress in alloy 617, you run into a real problem where you're actually post-weld heat treating between the solvent temperatures for the boundaries and the cores. So when of course, your post-weld heat treatment temperature exceeds the solvent temperature of the dendrite core, which has been reduced due to microsegregation during solidification, no gamma prime forms. And so this is probably like a worst case scenario for a post-weld heat treatment. So you need to be below the gamma prime solvents in the core, of course, and every other part of the microstructure, or above the solvents altogether. So here are a couple examples of that. And what I've observed in my post-weld heat treatment of just simple bead-on plate welds is that when you have these two-step post-weld heat treatments, I seem to find bigger and bigger discontinuous coarsening zones. And so these are a couple examples of the discontinuous coarsening we've seen before. In these micrographs, you can see that the a larger scale distribution of gamma prime has become more homogeneous, but in solving that problem, we appear to have made this one worse. So this is the situation with a couple different post-weld heat treatments. There's kind of no solution so far, although I think a proper homogenization, which is 1100 C for 4 hours. This is 1135 for 1 hour, based on the heat treatment given to the base metal. But as I think Dan or Professor DuPont are both mentioned, in order to completely homogenize the weld metal, 1100 C for 4 hours is the best heat treatment. So I think the best case scenario is 1100 C for 4 hours, followed by an aging, and at which point you may or may not still form precipitate-free zones or by discontinuous coarsening. So at this time, I want to go back to the stress relaxation cracking problem. So we've been over the post-weld heat treatments, and of course, so the best is probably homogenization, 1100 C for 4 hours, followed by aging. However, I want to, at this time, start talking about testing for this. And so as you look at this thermal cycle, you can think about the stresses that may go with it, and you can start to think about different like Gleibel testing approaches, right? As with any thermal cycle, so you can do this in the Gleibel. You could simulate a heat affected zone, or maybe you don't simulate a heat affected zone because your samples are taken from a weld, or maybe you simulate the homogenization and the aging before you start applying load to the sample, or maybe you apply load when you're cooling. And a lot of people have thought about this before, and they haven't really gotten to a point that they found really satisfactory. And I've tried to do different combinations of heating and loading at different times and different rates and all of that, and I was never really satisfied. What did occur to me, though, is that when you're holding a hammer, every problem looks like a nail, right? So I decided I wasn't going to use the Gleibel for this. I didn't think the Gleibel was really the appropriate approach. So I changed modes. We can go into the standard self-restrained versus externally loading testing debate. I changed approaches to self-restrained testing. And so this testing approach begins with compact tension samples, which are pre-strained in compression to create a tensile residual stress, which then relaxes upon further heat treatment or thermal exposure. So in this particular work, Mark Tursky and others out of the United Kingdom studied this quite thoroughly, and so they made an abacus model and measured the residual strain here and figured out the residual stress, and were actually able to, via some custom abacus subroutines, predict the rate and shape of cracking. And so their results from this are here. I didn't show the cracking in the abacus model, but they have creep cracking of about 2 millimeters, and this took them 4,500 hours. And so I think it was one of their remarks, or one criticism of this, is that they didn't generate very impressive cracking for such a long thermal exposure, and it would be nice to accelerate that. We have just a couple notes here. They did fatigue pre-crack one sample. This one was not fatigue pre-cracked, and that didn't affect the amount of creep cracking which occurred later. Also, they were able to monitor crack growth via potential drop, and I tried to build my own potential drop system, but that wasn't real successful. Anyway, my approach here is, so I wanted to do two things. I wanted to incorporate some sort of weld metal microstructure and subsequent post-weld heat treatments. And I also need to use thinner material. So my samples are actually 4/10 of an inch thick. But anyway, the fabrication procedure here was to make a weld on one side of my plates and then do different post-weld heat treatments, which we've already talked about, the microstructural results of these post-weld heat treatments. So, and then they're machined and pre-compressed and tested. So again, the procedure here is welding, post-weld heat treating, and then pre-compression. So in every case, I pre-compress them to 1 millimeter of plastic deformation. I simply measure that as the change in this gap. So the change in the gap here, I measure as 1 millimeter smaller plastically. And so, the thinking there is that these are different alloys and they're in different heat treatment conditions. But if you control the amount of plastic deformation, then, hopefully you have some sort of comparison between all these different conditions, even though the stresses are going to be different depending on the condition. So I think I jump right into results here. So I'm going to show more pictures, a bigger matrix, but this is an example of a creep crack on the edge, and you can see extending into the notch here. And so these samples were sectioned a little bit under this. I didn't do the normal sectioning procedure, which would be parallel to the plane of the page here, because there's a weld metal and base metal microstructure in every sample. So the sectioning is actually here. So if this is broken open this way and then sectioned underneath this, this is the resulting micrograph. And so you can't say anything about the extent of creep damage in the micrographs prepared for metallography because they're all going to be different distances from the main crack based on the topography of the crack. Measurements were also made. The extent of creep cracking, which is where the procedure for that is to make 9 equispaced lines and measure the length, and you average these and average that with an average of these. And anyway, that's how the extent of cracking is measured. Part of the goal here, part of the thinking with making a weld on one side is to, first of all, avoid the age-old problem of putting a crack in the heat-affected zone in a compact tension sample. And also in previous work, I had found some unbalancing of the crack front due to grain size variations. And so there's a case on the next slide where you can see that pretty clearly. So what I'm going to show is essentially this matrix, except in fracture surface form. So that matrix looks like this. This is just both sides of the sample next to each other in every case. And this is a lot of information to take in at once. So on a subsequent slide, we'll go over the numbers that you get when you measure the lengths of these. A couple things that you can only observe here is you may already be able to tell there's a pretty clear difference in structure size between the 740 samples and the 282 samples. So the 282, as you may have noticed, was tested in the aged and annealed condition, and that refers to the condition before welding. So this aging or annealing happened before welding, which was before post-weld heat treatment, which was before pre-straining. So that's a lot of steps to keep in mind. Anyway, before I move on, one thing to point out is that the unbalancing I was looking for only really occurred in this case where the creep cracking is obviously deeper in the heat-affected zone weld metal side of this aged 282 sample, which, if you think about the processing route here, makes a lot of sense to me because the sample was welded in the aged condition and then pre-strained in the as-welded condition. So this microstructure would have been weaker than the normal base metal due to the thermal excursion associated with the weld. Okay. So to quantify that, this is the results you find, and you can see in every case the 740 cracks way more, and I think that in general the post-weld heat treatments compared with each other have the expected trend of reducing the amount of creep cracking either by improving the microstructural condition or relieving some residual stress created by the weld. So part of the reason for the really, really extreme cracking in alloy 740 is this really almost anomalously large grain size. It's not anomalous for 740, but the grains are way, way bigger than 282 and 617. I guess the starting condition of 282 doesn't really affect the grain size, and since then grain size normally shows up to weld this way, this is another way to look at grain sizes as just backscattered electrons. So you can see even more clearly, I think, how enormous the grains are in 740, which, as I explained before, would lead to higher stress concentrations per boundary. The other problem with 740 is that there's going to be, way more interior gamma prime precipitation, interior relative to the grains. And so if you were paying attention to the gamma prime former contents, you'll see that gamma prime precipitation is much more intense in 740 and 282 than 617. So between the small grain size and the weak precipitation reaction, I intuitively would expect 617 to be the most resistant to cracking. Regarding the grain size themselves, I think some very simple thermodynamic calculations, just step calculations here, and then the same thing here, including borides, show that there's not a lot happening in 740 which could pin grain boundaries, and so it has these really, really huge grains. So there's a lot to talk about in a slide like this, but the reason I have it is because a couple things to mention are that what happens in the pre-compression is you essentially reduce the creep ductility. And so if you have a very creep-resistant material like 282 or 740, which had much higher creep rupture performance, you've consumed some of their creep ductility in the pre-straining. If your material is much more ductile, you've consumed less creep ductility in the pre-straining, and it therefore has enough ductility to relieve residual stresses. So that we come to conclusions which pretty much just summarize what I said. This pre-compressed sample approach effectively generated cracking by stress relaxation because there was no other loading. Welding the one side of the sample, though, I don't think was that good of an idea. Grain size appears to be king in this testing. Intergranular precipitation following that. And so the big problem which we're fighting here, this isn't like a conclusion of this work, but an overall big picture perspective is that the strengthening mechanisms put in place to improve the creep life are also making it more difficult to relieve residual stress, and which is why we're, I think, probably going to see more of this relaxation cracking in the future. So that's what I have today. Thank you.